Okay, so I guess it's recording. So fingers crossed on the audio. I don't know if y'all noticed last time, but the audio didn't take yesterday, and I don't know why, because it did take the day before that, and I don't know what I did in the audio settings. Some of y'all may have seen I have my audio guy on the problem. Okay, so last time we were talking about Gauss's divergence theorem, and here it is, various different forms, various different ways to think about it. This is, I think, ultimately the best conceptual way to think about it, and that is that flux is an integral of flux density. Flux, believe it or not, intuition or not, it behaves like stuff. It behaves like mass, or something like that. So in the same sense that mass is an integral of mass density, so is flux an integral of flux density. Now you can think of flux, again, several different forms of thinking of flux. Flux density, again, you can think of in several different forms. You can think of it as divergence. You can think of divergence as del dot, the vector field. Ultimately, though, what you're doing when you're talking about Gauss's divergence theorem is you're computing a flux as an integral of flux density. And I think that's powerful intuition and really important to carry with you. Okay, so we talked about how that fits in on the diagram, and we did an example. And we're going to move now to making some interpretations with some physical applications. Real quick, I will point out today is going to be another one of those days where I bounce back and forth between my 212 notes and my 219 notes. And again, ask me at any time, where are we in which file? And I'll be happy to clarify. Okay. So, let's talk about how fluids move. Keep in mind, that's actually the most convenient metaphor, physical interpretation for what flux is. Flux is fluid passing through a surface. That's, quantity of fluid per unit time passing through a surface. That's what it is. So, I make the observation here that if you know the flux, you know how much fluid is flowing out of a region. Well, wait a second. If I've got a region and I know how fast the quantity of fluid is flowing out of the region, well, that's telling me how fast the quantity of fluid on the inside is decreasing. Right? Quantity per unit time exiting is the same as quantity per unit time of the total decreasing. Does that make sense to everybody? I think it's pretty plausible if you really kind of think about it. It's almost just a rephrase in a way. So rate of change of the quantity on the inside, but we put a minus sign out here in recognition of the fact that a positive flux, being outward oriented, positive means that you're going to have a negative rate of change of the remaining quantity inside. So this is going to be my starting point here. Oh, and this K, if I can get, oh my gosh, that little button, always a problem. This little K right here is, I have to throw that in there just for units reasons. And again, I don't want to worry about units in this class. That's somebody else's problem. You'll deal with that later. But point is, it's some fixed conversion of units. Okay, so with this formula in mind, now this is a global statement about the total flux and the total rate of change of quantity. So now I'm going to say, let's basically divide by volume, right? And what happens if you talk about flux per unit volume? Well, that's flux density. That's divergence. And now, likewise, what happens if you take mass and divide differentially per unit volume? That gives you density. Everybody with me? So this gives us an alternative interpretation of divergence in the same sense that flux tells you how the total quantity on the inside is changing. Divergence, at a particular point in that interior, tells you how fast is the density of fluid at that location decreasing. Does that seem kind of plausible? Right? So again, keep in mind, in some sense, what divergence measures is to what extent is the fluid kind of doing something like this. It measures sort of outward flow away from a given point wherever you're computing divergence. So, well, this is telling you two things. On the one hand, this represents divergence, right? That's sort of the generic picture of what divergence looks like. But this also is telling you how fast the amount of, the density of stuff in that general vicinity is going down. Because if this is a picture of what your fluid is doing, the fluid is leaving that general area. The density remaining in that general area has to be going down. So same basic idea, just sort of locally instead of globally. All right. Okay, so now that is one interpretation of how to think about flux and divergence in terms of fluids. Now here's a different one for a different kind of a fluid. And this is a weird thing to think about, but there are importantly different kinds of fluids. Here we're talking about a fluid that is neither created nor destroyed. It's there's a fixed amount of fluid, right? And it's kind of flowing around, and there might be more of it, there might be less of it. But a pretty good metaphor for this is maybe if you think about we've got mosquitoes in this room, and they're kind of flying around. Right, and there's only so many mosquitoes. And if I consider, let's say my general vicinity here, I might be particularly interested in how fast the mosquitoes are flowing out of my general vicinity, because that lowers the mosquito density, which is a good thing. Right? But there's a fixed amount of mosquitoes. The mosquitoes are not spontaneously generating out of nothing. And sadly, they won't just disappear, just magically into the void, right? Wouldn't that be nice? I'd buy one of those at the hardware store. So here's a different kind of fluid, though. So what I'm going to call an incompressible fluid. And so, in other words, I don't want to entertain the possibility of this fluid changing density. Now, what could such a fluid be? And I claim that we are currently surrounded by one such fluid, and that is the flow of photons in this room. Right? We've got a bunch of light bulbs up there. There's a bunch of light coming out of the projector. There's photons flowing all around the room. Right? But density is not changing at all. Right? If you look at how many photons there are in this little ball that I've got my hands around right here, how many photons are in there? Well, they fly in, they fly out, right? Sure, but it's not like they're collecting. It's not like the number of photons in this little vicinity right here is collecting, and there's more and more and more, or less and less and less, right? Take the light bulbs. Photons are shooting out of the light bulbs. Is the light bulb going to run out of photons? No, it's creating photons. Right? So totally different kind of fluid. We have a fluid here that can appear or disappear. It can be created or it can be destroyed, right? When a photon hits some dark surface like this right here, the photon hits it, it doesn't bounce off. It just kind of gets absorbed into it. It turns into heat, right? But it disappears. Right? So again, sadly, mosquitoes don't behave like that. Photons do. So, different kind of a fluid. Now, how would I interpret then if I have this photon kind of a fluid? Totally different fluid. Now, what interpretation would I make of this? Right? This generic picture of divergence. This is showing a positive divergence at that point. What does this mean physically? What's happening here? That's a light bulb. Again, light bulbs don't run out of photons. The number of photons in that general vicinity at that point is not decreasing. What this positive divergence represents is that this is a source of photons. That's where photons are being created. Does that make sense to everybody? And now, but just on the flip side, let's suppose that I had something that looked like this. Maybe this is the flow of photons. And if I were to ask, okay, well, what's going on at that point? Right there, are we collecting photons there? Is the number of photons in that area just getting more and more dense? And pretty soon we're going to have a great big ball of photons? No, of course not. That's not how photons work. If photons are all going into a vicinity and not coming out, they're disappearing. In the same way that water kind of disappears when it goes down the sink. Thus the term sink. So for this different kind of a fluid, an incompressible fluid, so the density is not allowed to change. Again, kind of like photons. Divergence, well, here I'm talking about flux, but flux, of course, flux per unit volume is all divergence is. So in the same sense that flux, being positive or negative, distinguishes source from sink, so does divergence, being positive or negative. It tells you locally, at a given point, are photons generally being generated at this location, or are photons generally sort of disappearing at this location? Is everybody okay? All right. So this can be kind of confusing, thinking about these different kinds of fluids and how to interpret flux and divergence accordingly. So you got to give that a little time to sort of sink in, no pun intended, half intended. Okay. Right. So next thing, I'm going to flip out of my 212 notes. I'm not going to talk about this page because I'm going to cover that in my 219 notes. This page here, I'm not going to cover at all. This is a highly optional thing that, frankly, it's mostly a physics argument, and it has a sort of a vague connection to math that I think is fun, but in a time is tight scenario, I don't think we quite have time for this. So conceivably, I might come back to this later if we just have a bunch of time at the end, which I'm not expecting. This page here, again, I'm going to cover in the Math219 notes. I'm going to cover it a little bit differently, a little bit more efficiently. This page here, again, highly optional. Not going to cover this page either. So you're not responsible for this page. But again, it's pretty neat. If you're curious, there's this interesting phenomenon that if you have a spherical shell on which you have either charged particles, or maybe if you have a spherical shell that's large enough to create a gravitational field, it turns out the field on the inside of the spherical shell is flat zero. It is a weird little sort of phenomenon of geometry. Ultimately. And best way to see this fact that I'm aware of involves a heavy use of the ideas that we've been talking about of flux and divergence and the divergence theorem. Again, you're not responsible for that page. And there's some discussion of Maxwell's equations here. Again, I'm going to cover that differently, and so skipping that page as well. So I'm going to, for the moment, I'm going to put us onto this page, but I am going to skip over, though, to my 219 notes and talk about the physical examples here that I prefer to do here as opposed to the 212 notes, as I just said. Okay, so this is in the 219 Chapter 7 notes, page 21. Okay. All right, so let's talk about a light bulb again. Right? You're going to do just a sort of a different take on the light bulb example. So here's our light bulb. I'm going to color our light bulb orange. I would do yellow, but it doesn't show up very well. So light bulb, of course, has a bright spot at the center. That's where the actual bulb is, or I guess the actual LED these days, right? Little teeny tiny little itty bitty little thing, but it shoots out the photons. And then the photons flow out like this, roughly, right? They always flow outward, of course, and then etc. Now, I draw these field lines smaller as they get further out because the light is dimmer. It's not that the photons are moving slower, it's that there's kind of less photons out there because they spread out as they get farther and farther away. Said differently, if you have a flashlight shooting out photons and you shine it up against the wall, there's a certain amount of brightness. If you back further up, get a greater distance from the wall, the bright spot is not as bright. Right? Everything spreads out. Does that make sense to everybody? There's sort of less overall flow out there. Okay. All right. So let's talk about what's happening at the bright spot here, at the point where the LED is. And let's think about a little ball around that bright spot. And how much flux is there through that little ball? Wow. Gosh, there's going to be a lot of flux through there. Another way to say this, how many of the photons coming out of that LED are going to pass through this sphere surrounding the LED? And my answer is all of them. All right? If you've got a little LED and you surround it with a little sphere, the photons have to come out through the sphere. So 100% of the photons coming out of the bulb go through this sphere. So what's the volume of this little sphere? Well, it's small. It's a small sphere. In fact, let me draw it a little smaller just for the effect of it. We'll draw it with a little orange circle here. I can make that as small as I want pretty much. I mean, eventually the bulb itself has a finite size, but I can make that a very, very small little sphere. So divergence being flux per unit volume, we have a significant flux because all of the light bulbs count in that flux. We have a very small volume, and therefore flux per unit volume, aka divergence, must be huge. Large flux divided by small volume gives huge flux density. You buy it? Okay. All right, so that's what's happening there. And in fact, why don't I go ahead and leave this like so. Okay, now let's talk about what's happening here at that point. And I want to talk about the divergence at that point. So I'm going to again start by talking about flux. We're going to make a little ball there. And I'm going to ask rhetorically, what is the flux of photons through that sphere? And, well, I claim it's 0. As follows. Any photon that enters that sphere subsequently leaves the sphere. For every photon flowing in, there is a photon flowing out. So grand total, 0. Does that make sense to everybody? Because, I mean, let's face it, there's no light bulb inside of that little green sphere, right? The light bulb is over there at the center. Inside of this little offset green sphere, there's no photons originating there. So anyone that flows in, flows out. That cancels. Grand total flux is 0. And if flux is 0, then certainly flux density. Whoops, wrong color. And actually, you know what I'm going to do? I'm going to cheat and do that. So flux density at that point is 0. Everybody happy? So a couple things I like about this. One is you can see how divergence actually directly points to where flux is happening. Right? I mean, now again, how do we think about flux? You might say, well, generically, if I have this large sphere here, maybe this is the outer bulb, the outer glass of our light bulb. And if I measure the flux here, and if I know what this flux is, where's that flux? Very tempting, again, just because of measurement. We say, where's the flux? Oh, well, I just measured the flux on the sphere, so that's where the flux is. But with this physical example, I think you can see that's extremely naive. There's no light bulbs originating on that sphere. The light bulb at the center, right, the orange spot, that's where the photons are coming from. all this flux that you measure on the outer sphere is just detecting what actually was happening on the inside. Right? Remember, I made this pitch that I know it's weird to think of it that way, but we think of flux as being a kind of a stuff. You measure it on the outer surface, but it's actually accumulating from the inside. And this is a wonderful physical metaphor for that. Very large value of divergence at the center points to the fact that that's where the photons are coming from. That's where the flow is coming from. That's where ultimately this flux on the outer sphere is coming from. And it's not coming from there at all. The flux that eventually passes through the purple sphere passes through that green sphere, that green vicinity, but it didn't originate there. And divergence, again, perfectly measures that. The fact that the divergence is 0 here is the indicator that, that's not where the photons were coming from. How we doing? Is everybody okay? All right. Okay. All righty. Let's see here now. Again, with the eraser, this thing keeps migrating. Let me fix that. Okay. Much better. All righty. Here's a different kind of a fluid coming up. Let's talk about a gas and exactly how this scenario gets created. We have some flexibility. I'm going to say, let's suppose that we have a balloon. I'm going to make it red because a lot of balloons, nice pretty red balloon. And let's suppose that that balloon is expanding. And not because we're blowing air into it, but because I have this red balloon, nice pretty red balloon, right? And I'm going to suppose that the temperature starts to increase. And I don't know how much y'all know about physics, but when you have a gas, how many people have seen the ideal gas law in a high school physics class? Some, not all. Okay, that's fine. When a gas, when the temperature increases, the gas expands. Right? Okay, so I'm going to suppose that that's our scenario. We have a balloon full of gas, and it starts to expand. Well, due to a temperature increase. When it expands, the air on the inside of the balloon expands along with it. And I think you'd probably believe that the air that's close to the outer edge of the balloon is going to be moving kind of right along with the balloon. Whereas certainly the air at the very center doesn't move at all. And then kind of interpolating between those, the air that's kind of closer to the center, well, it moves a little bit, but not as much as the air that's further to the outside. And so altogether, I claim that when you raise the temperature inside of a balloon, roughly speaking, the flow field is about like this. It's proportional to the position vector. In other words, the further you are away from the origin, the faster you're moving away from the origin. Everybody okay with that? Seem kind of believable? All right. So, okay, now what I want to do is I want to consider a fixed sphere here. And I want to talk about the flux through that fixed sphere. All right, so we've got this, the air is moving, and the air is, sort of moving outward. It's going to be moving through that purple sphere. You know what? Let me make this a little bit easier to see there. So there's our fixed sphere. The air is expanding. There is a flux of air through that sphere. And of course, what that means is there is fluid that is exiting the sphere. Again, that's what flux is. Flux is fluid passing through the surface. So this is fluid exiting the surface. Now, I can write down Gauss's divergence theorem. There it is. There's Gauss's divergence theorem. I can take this. I don't know what I did there. I can take this vector field, F. I can compute its divergence. and the divergence ends up being that number. That's just a little algebra calculation, something that y'all can go through and confirm yourselves. I encourage you to take a whack at that, right? How the green formula there, when you compute its divergence, gives you 3 times k. Nice exercise. Think about it. If you get stuck, if you're not sure how to, if you're not sure how to get started on this, or if you don't get this answer or what have you, come talk to me in office hours. It's no big deal. I'll be very happy to show you. Anyway, the answer ends up being 3k. So what sense do we make then out of this statement that flux is triple integral of 3k? What does this 3k mean on this picture? And, well, I claim that this 3k, oh, you know what, bad color choice. Let me do this in the dark blue again. This 3k, being the divergence, being a constant, tells me that the density of the air on the inside is decreasing at the same rate everywhere inside of that purple balloon. Right, now, again, let's pause for a second and think, wait, right, reminder, what's going on here? We've got this purple sphere, and we agree that there is flux of air going through that purple sphere. The total amount of air inside of the purple sphere is decreasing. Well, if the total is decreasing, that means that the average density is decreasing. What this is telling me is that locally, specifically locally, the density is decreasing at the same rate everywhere. The divergence is telling you at any given location, let's say right there, for example, how fast is the density of the fluid changing at that point? And then if you compute divergence there, that's telling you how fast is the density decreasing at that point. So being it is a constant, that means that at these 2 points and at every other point, the density is decreasing at the same rate. Now again, pretty plausible, pretty believable. That'd be a pretty weird balloon where there's a lot more air on one side of the balloon than there is on the other side of the balloon. That's not how gases work, right? This is, again, sort of consistent with intuition. This is kind of what ought to happen. And so this is a sort of a plausibility check for this other kind of fluid thinking in terms of the divergence there. How are we doing? Everybody happy? Questions? Feel free. Let's do it. Hit me. Everybody's happy? Okay. All right. Okay, so 2 different kinds of fluid. Here's the weird thing. Sometimes a fluid has both of these features at the same time. Sometimes there is a fluid where the total amount of fluid might be changing. But also, the fluid might, in addition to that, be being generated, like a light bulb. Right? So you could have a light bulb kind of fluid that is also, to some extent, a sort of an air kind of a fluid, and you have both. So the argument I like to make about how to deal with this, and now this is just kind of for your broad liberal arts education. If you're not going to use it, it's for general preparation for your future. If you are going to use it, engineers, by the way, I think you'll probably have to take a fluid dynamics class at some point, so you're going to see something along these lines. But when you generate fluid, there's really only 2 possibilities of what can happen with that fluid that gets generated anywhere in your story. If fluid gets generated, it either sticks around, in which case the total amount of it increases, or it doesn't stick around, it departs through the boundary and therefore becomes flux. So that's it. Either it stays or it doesn't stay, and therefore the total of those 2 possibilities has to be the total rate that you're generating fluid. Reasonable argument, I hope. So again, as we've done before, I'm going to then say, okay, well, this is a global statement. This is about, overall over the whole region. Now let's just say differentially per unit volume. And flux per unit volume is divergence. Mass per unit volume is density, right? And then a weird thing happens over here on the right. Generation rate, total amount of fluid being generated per unit time. If I then say, per unit volume, I'm just going to call that generation rate density. I don't know how to make that as more physically relatable. I guess you could say, if you have if you had, let's suppose a cloud of glowing gas, let's just say, right? Then where there's more cloud of glowing gas, there's more photons being generated per unit volume, and so you'd say there's more generation rate density there. That's just an example, one way to think about it. Anyway, point is, in such a question, you can write down this equation, and presumably if you know this, and if you know that, so for example, if you know the vector field that's being created by your scenario, then you can compute the divergence. If you know where fluid is being generated and by how much, then you know that, and then you can solve for, okay, how is the distribution of fluid going to be changing with respect to time? Okay. All right. Now, again, this is highly supplemental. Don't worry about the details on this. I just wanted you to know that this can happen, and this is how you deal with it. Okay, different physical example now. I want to talk about gravitational fields. Y'all probably, most of you anyway, have seen the idea of gravity, certainly physically. Certainly we all have a life experience with gravity. The gravitational force, inverse square. I think most people have seen that. And then, of course, earlier in this class, we talked about the gravitational field, which I initially wrote down with that formula, but which I think is actually a little bit more intuitively satisfying with this formula, because in this form, you can see the inverse square aspect of the magnitude, and you can see how the direction is radial. So when we say that a gravitational field is inverse square radial, we're just observing what this explicit formula for the vector field is saying. That's all. Is everybody happy with that? Okay. Now, again, there's different ways to treat this mathematically, and real quick aside. When we write down this formula, this is an idealized formula. That's not how the actual physical universe works. The actual physical universe doesn't have point masses, right? Mass is usually a lump. I can have an amount of mass in my hands, but it's usually a rock that's got some volume to it. If the entire mass of a rock were in a geometric point, the density would be undefined. It's just not how mass works physically. So this is an idealized scenario. Okay, but for practical purposes, it's surprisingly effective. So, here's the thing. This formula, gravitational field being inverse square radial, that is just like a point light source that we talked about on the previous page. It's the exact same scenario as this right here. Point light source, if you're twice as far away, it's going to seem 1/4 as bright. Now, another way to say it is, if you look at a sphere of one size and then you look at a sphere twice the size, the amount of flux through each one of these spheres, well, total amount of flux is the exact same on each of these spheres. How many of the photons go through any given one of these spheres? All of them. Every photon goes through the first sphere, every photon goes through the second sphere. So the total flux is the same, but the bigger one has 4 times as much area, which means that the number of photons per unit area is 1/4, right? Is that everybody okay with that? So inverse square radial, and again, as we've just seen here, as we were just reminded here, gravitational fields, inverse square radial. So here's the shocking and powerful conclusion. You can think of gravity as being communicated between pieces of mass by little particles. Right? Now, we don't normally think of this. Normally, I think of gravity as this, well, it's just this ever-present, everywhere thing that keeps me hurtling constantly toward the ground. Right? It's just a force that kind of, it's almost a little magical in a way, right? That, the mass that's attracting me is way, 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 way down underneath the surface. Most of the mass of the Earth is very far away from me, and I'm just magically being pulled, right? And it just happens, right? It's just some sort of ethereal thing. What this is pointing out is that if you were to think of gravity as being communicated by little particles, that every piece of mass, it doesn't have a gravitational field. It's emitting little particles that hold gravity in them. And we usually use the word gravitons. If you think of gravity as being communicated by gravitons, the algebra is exactly the same. In the same sense that light bulbs emitting photons, right? Well, likewise, mass emits gravitons. Weird way to think about gravity. But again, the algebra lines up perfectly. So very useful. Now, to the question of, is this real? Is gravity, is there really such a thing as a graviton? If you ask a physicist that question, you're not going to get a particularly crisp answer. It's going to be a long, complicated, sophisticated, practically impossible to follow conversation. At least that was my experience. So, keep in mind, physics as a science is something that's constantly being explored and understood better and better, but they don't have answers to everything, right? And I guess the takeaway that I got from my conversation on this with a physicist is that, they don't really know for sure. Depends on what you mean by exist. You know what I mean? One of those kinds of things. My point of view is it doesn't matter whether they exist. So y'all have heard me say this before, and I think this is a good thought. So we've talked about how, flux behaves like a physical stuff. Whether it is or isn't doesn't matter. The point is, if you pretend that it's a physical stuff, you're going to come up with right answers because it behaves identically as if it is, and so you might as well view it that way, right? And so you can get away with thinking of boundary flux, outward-oriented boundary flux, as being like a physical stuff. And so likewise, gravity may or may not actually be communicated by gravitons, but go ahead and just pretend it is, because it works like the algebra is going to work out the same anyway, and so you might as well pretend that gravity is treated by gravitons. Does that make sense? Okay. All right. So this allows us to actually write down some pretty cool stuff. Just by this metaphor. And again, so I'm going to think of gravity as being communicated by emitted particles called gravitons. And so let me talk about this equation right here then. This equation right here basically says, well, if every little piece of mass is emitting gravitons, and if these gravitons are shooting outward, they all have to pass through your surface. Right? I mean, here's a piece of mass inside of your surface. This little piece of mass emits a graviton. It doesn't really matter what the shape of the surface is. How many of those gravitons are going to go through your surface? All of them. It's inside and it's got to get out. It passes through the surface. So more mass, more flux of gravitons, or what we call gravitational flux. More mass, more gravitational flux. The detail here of this constant is, again, that's just constants. Don't worry about it. It's a physics thing. It's not hard to prove that this is the right constant. That's just a matter of looking at this constant in here and making a more detailed argument than I'm doing here that is, again, not really it's a distraction from the point I'm trying to make. So anyway, there is a constant there, and that's just details. Don't worry about it. But the big point, again, more mass, more flux. Is everybody okay with that? Well, golly, we're actually kind of already done with the point here because mass is a triple integral of density dV. That's old news. Colors. The constant being the same on both sides. Just to, again, you got to be legal about it, right? But mass is triple integral of density. And of course, flux is a triple integral of divergence. That's just Gauss's divergence theorem. So those sort of the horizontal parts of this little square of equations. The horizontal parts are, mass is an integral of density, flux is an integral of flux density, not much happening there. But look what this means then. That means that these two triple integrals are always equal, no matter what your domain is. How could that be possible? How could two triple integrals always give the exact same value no matter what domain you integrate over? And I propose the highly plausible answer is, well, it just must mean that these two things here are equal. And so this gives us a nice interpretation of gravitational divergence. Gravitational divergence is proportional to mass density. Now, if you were to try to prove this, directly brute force. If you were to say, okay, well, look, I've got a bunch of mass. Let's look at that table, right? This table here. Well, there's a bunch of mass on this part of the table, and there's a bunch of mass on this part of the table. If I wanted to understand the gravitational field at this point right here, well, there's gravitational field pointing me toward that mass, but there's also gravitational field pointing me toward this mass. There's bazillions of little pieces of mass. Each one is going to exert its own different, not only different magnitude, but different direction gravitational field at this one little point that I'm interested in understanding. It's a preposterously difficult calculation just to find the gravitational field itself. That alone would be a hard calculation. And then you're saying you want me to compute the divergence of it? Wow, that seems really hard. So again, independently, this is a very hard calculation, but we come to this conclusion that gravitational divergence is proportional to mass density in a snap, and it comes from two things. One is this idea of recognizing that gravity is kind of like light bulbs. Is a huge observation. Really important piece of intuition. Gravity is kind of like light bulbs. Just gravitons instead of photons. But other than that, it's pretty much the same. And the other big point here is the divergence theorem. Without the divergence theorem, we would not have been able to make this connection. And so this very powerful conclusion depends critically on this big theorem. Everybody happy? Okay. All right. Let's talk about electric fields. Now, this might be a lot more relevant, actually, to a lot of y'all. If you're not going to be an astronaut or a cosmologist, case could be made that it's a safe approximation to just treat gravity as being a constant near the surface of the Earth, and so who really cares? We don't need to study constant gravitational fields. That's easy. So case could be made that electric fields are much more complicated in everyday life. And they're inside of all of our electronics. They're hugely important in how those electronics work. It's just a tremendously big deal. Here's the wonderfully good news. It's also inverse square radial. just like gravitational fields. Now, the difference is it's about charge instead of mass, and there's a plus and a minus. Yeah, there's differences, of course. They're physically different. But structurally, other than constants, it's pretty much the same as a gravitational field. And so in the same way, then, electric fields can also be thought of as being communicated by little emitted particles. They're not called gravitons, of course. You'd think, because it's an electric field, that you'd call them electrons, but you can't because that word's already been used. Doggone it, right? That's a bummer. If you do want to talk about an imaginary, possibly fictitious particle that communicates the electric field as a flow of these kinds of particles, the common word that people use is photons, which I also find confusing because, again, that's another different thing. But anyway, so let's not worry too much about that. The point is, it's communicated by a flow of little particles, and so I can make the exact same argument. More charge, more particles, photons, whatever. More particles means more flux, because every one of these emitted particles has to leave your boundary surface. So again, the proportionality constant, and here we go again. I'm about to run out of stylus. This constant is not our problem. We're not going to worry about it. Again, though, charge is a triple integral of charge density, dV. Again, same constant on either side, just to be legal. Right? Also, again, Gauss's divergence theorem. Flux is a triple integral of flux density. And so, again, we get a nice conclusion. And really interesting fact. And while, again, the electric field oh my gosh, it's covering half of my screen. Settle down. Okay. Even though the electric field itself would be really hard to compute if you have a bunch of particles, if you have some sort of a distribution of charged particles, hard to compute the electric field. But the divergence of the electric field is easy to compute. It's just proportional to how many charged particles per unit volume are there in your vicinity. So that part's easy. Anyway, again, powerful fact. How we doing? Everybody all right? Okay, so back to the Math212 notes. Looks like we're on page 238 here. So I want to talk about Gauss's divergence theorem in 2 dimensions. Of course, the divergence theorem we've been talking about up to now has been the 3-dimensional version. And yet, we've talked about flux. And there it goes. Stylus is now out of juice. Let me plug it in. I might get to use it again in a few minutes. Let's see here. How do I do this?
Wait, what's the clip for?
That's to keep the little piece of rubber on here. The little piece of rubber is to help, for one thing, it gives me more to hold on to, but it also helps me. I can use finger memory then. I can feel where the eraser button is. And so that just saves me precious seconds, so I don't have to constantly be like, I can't see the thing, you know. So that's just the awkwardness of having bad eyes, basically. Yeah. Okay, so we have previously talked about flux through a curve, right? And flux through a curve was a calculation that we did. We found ourselves writing down an expression that looks kind of like this, and we weren't sure how to compute that thing, though, because, golly, we've never seen anything like that before. And what I did a while ago is I made a clever argument about how if you rotate everything 90 degrees, then that n becomes a tangent vector, and this becomes a vector line integral, and we can talk about Green's theorem and circulation, and we ended up, playing that through, and we ended up getting a little result. So here I'm going to treat it differently. And I'm going to say, okay, well, if we're interested in two-dimensional boundary flux, then it's an accumulating quantity. Whoops, well, that's fine. Two-dimensional flux, boundary flux, is an accumulating quantity. And here's the argument. Let's see, now again, I need to clean up the picture. Okay, let me come back to, yeah. So if I were to look at the whole, right, there's two-dimensional boundary flux through the boundary curve for the whole. Now let's look at the left side. For the left side, we'd have that. And then for the right side, two-dimensional boundary flux would be like that. And is the whole the sum of the parts? Well, a lot of it lines up. A lot of it seems to be working well. Oh man, that's not what I wanted to do at all. That lines up nicely. That lines up nicely. That lines up. That lines up. It's all looking good except on that curve right there. Right, that curve right there in the middle, that's the one where, yeah, there's no purple. There's green flux there, there's blue flux there, but there's no actual whole, purple outward-oriented boundary flux happening on that red curve. So that seems to be the sticky wicket. That seems to be the problem, is this right here. This is the discrepancy, you might say. And that said, even though that is a discrepancy, the integral along this red curve in the green direction and the blue direction are exact opposites of each other. They're negatives and they cancel, and therefore there actually is no discrepancy. And outward-oriented boundary flux in two-dimensional regions, again, is an accumulating quantity. Everybody good? You'll notice I went through that argument pretty quickly. It's because we've been through that argument a bunch of times already, right, in various different contexts. It's one of the kind of beautiful things about this subject is the arguments that we make in these different contexts are so similar to each other because they are ultimately all the same theorem, just applied in different contexts. Okay. All right, so we have an accumulating quantity, and so yeah, the whole, if I'm interested in two-dimensional outward-oriented boundary flux, the whole is the sum of the parts. Total accumulating quantity is the sum of the pieces of accumulating quantity. As we've done a few times in the past, we can multiply and divide by the same thing, perfectly legal, nothing, no problem generated there. Then we look at this expression on the right, as we've done in the past several times, and we notice that, hey, we have a Riemann sum there. We have a limit of a summation of some expression times area. That's literally a double integral Riemann sum, right? That's why we have a double integral here. And the only remaining question is, what is this integrand? What does this here turn into? And again, this is a calculation that's all details, and it's I don't think it's a good investment of our precious time in this class, but that integrand turns into this expression right here, which you'll recognize. We previously saw this statement here. Whoops, that's not the color I wanted. We previously saw this equation here as an adaptation of Green's theorem, right? And we wrote down this exact formula by looking at the left-hand side and turning everything counterclockwise and tangent vectors and dx differentials and Green's theorem and blah, 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 and the exact same thing come out. Here, I'm viewing it instead instead of sort of piggybacking off of an existing accumulation theorem, here I'm presenting this as its own separate accumulation theorem. Okay. Everybody okay with that? Whoa, what did I just do? Oh, it's moving my... Okay, yeah. There we go. Okay. All right. So, finally done with Gauss's divergence theorem. We're going to move on now and talk about Stokes's curl theorem. Let me just remind you, let's see here, come to think of it, I will go back to the diagram real quick. Where did I put, I didn't realize it was this far back. Come on, there it is. Okay, so here's our three-dimensional diagram. We just got through talking about Gauss's divergence theorem. Notice that it has the same structure as the fundamental theorem of line integrals in the sense that right, left, evaluate on both sides, you get the same thing. And likewise over here, right, left, evaluate on both sides, you get the same thing. Right, so diagrammatically, Gauss's divergence theorem and the fundamental theorem of line integrals are exact same thing, just different details, different context, but it's morally equivalent. Right? So that said, we are now, again, we'll be looking at Stokes's curl theorem. Here's where it's going to be. You could probably guess what's going to happen. It's going to be the exact same thing. We're going to entertain a surface and its boundary curve. We're going to think about line integrals of a vector field over that boundary curve, and we're going to try to figure out how to interpret that as being, and I am making a bit of a mess here, we're going to try to figure out how to interpret that as being a flux, apparently. So saith the diagram. Right, just kind of following. The diagram's doing all this bookkeeping for me. It's keeping track of what I ought to expect to happen. And the diagram seems to suggest that we're going to be turning this into a flux over our original surface. And the question is, what is this operator that tells me what the integrand will be? And now, of course, you can see what the answer is here in the diagram, but we need to make sort of, some sense out of that. And the punchline will be, indeed, that the circulation is a flux. So that's what we should expect, right? Now, that said, let's actually see that happen. So we're going to be thinking about a surface in space. The boundary is a curve. We always have orientation questions come up when we talk about boundaries. We have to, remember with Green's theorem, it always goes, I'm going to air quotes, say counterclockwise, right? With the Gauss's divergence theorem on the boundary surface, it's always, again, air quotes, outward, away from the solid. Right? Certain conventions about how we, what do you mean when you say boundary? You're talking about some sort of an orientation. What orientation do we mean? So here's the arbitrary but standard and therefore non-optional, right? Convention on how we orient boundaries of surfaces. Here we go. So, why am I in that mode? Okay, so here we go. Suppose we have a surface. And that surface is oriented. Keep in mind, an orientation on a surface means which direction through the surface are you calling the positive direction through the surface? Here I'm describing that with my normal vector pointing upward. So oriented surface. Everybody with me? The boundary curve. Okay, well the boundary curve is clearly that green curve, but which way should we go? What's the correct direction? What is the induced orientation on this boundary? If I've got an oriented surface, that should imply an orientation on the boundary curve. That's what we call the induced orientation. Which way should it be? There's two. It could be back toward me or over away from me. Which of my two options is it? Okay, so here's the convention. And by the way, there's a bazillion different ways to say this. I'm going to show you the one that I think is the most convenient overall. Yeah, there are other options, and if you have a preference, that's cool, as long as it's right. But I think this is the easiest one to understand. So what you do is you take your normal vector on your surface. You use your right hand, arbitrary, right? There's no subtext there. But you use your right hand. You point your thumb of your right hand in the direction of the normal vector, this being up. You'll notice my thumb is pointing up. Notice then that your fingers of your right hand, bending the way fingers want to bend, no hand yoga, right? But bending the way fingers want to hand, they point in a certain direction around your thumb. And in this case, they sort of point around that way. And this defines what I call a swirl. So a normal vector on the surface defines a swirl. Think of the swirl as being like a little hurricane on the surface that's going around in a certain way, right? And so then what you want to do is ask yourself, as this normal vector approaches the boundary, how does that sideswipe the boundary? So think about this little purple vector, and I claim the purple vector is going to sideswipe up against the boundary going that way. Right? As the hurricane approaches, which way do the leaves fly that are being torn off of the trees? Right? I mean, they're gonna go as I have it drawn there. Does that make sense to everybody? So that's the convention. That's how you decide what the direction is on your boundary. This is the induced orientation on the boundary. Everybody see the rule? So now, just as an exercise, let's imagine if let's suppose that the surface was oriented the other way. Let me erase all of this. Let me get rid of that and that and okay. All right. Hypothetically, what if the orientation on the surface was downward? Right? Well, downward, fine. Right hand, thumb in the direction of the surface's orientation. Now downward. Now look at my fingers. See how my fingers are now kind of rotating the other way. I mean, it's still my right hand. It's still the same in some sense, right? But it's, as seen on the surface, the swirl would be kind of like that. Everybody see that? And that means that that would sideswipe that way, which of course is the opposite of the orientation we got when the surface was going upward. Everybody happy? So what I like about this is it's perfectly easy to hold your right hand with the thumb up. It's also perfectly easy to hold your right hand with your thumb down. Alternative points of view involve imagining that you're walking along that boundary curve, but that you have to have your head pointed in the same direction as the surface orientation. And then if that's downward, then I've literally seen students during an exam. They're like, okay, let's see, I have my surface here. Okay, now I need to, here I am walking, right? And it's just super weird and confusing, and I think you can get yourself into a lot of trouble that way. So, but much easier just to do this, look at your fingers, boom. Okay. All right. Okay. Yeah, this is going to, by the way, smack heavily of Green's theorem. as it turns out. Specifically, the quantity that we're going to be computing here. Now we've got a surface, we've got its boundary, the accumulating quantity, the hopeful candidate, accumulating quantity, boundary circulation, just like with Green's theorem. By the way, a lot of people think of Stokes' theorem as being like it's kind of like Green's theorem in space. And that's a perfectly reasonable point of view. So boundary circulation, and again, even though it's computed on the boundary, I claim that it actually accumulates over the interior. And again, how do I know that it accumulates over the interior? Well, we're going to play the game. Here is a whole surface. Right, and I can suppose that surface is oriented some way. Let's say it's oriented like this. And let's ask, what would the boundary circulation look like? And again, look, you can make this algebraic, but we don't really need to. What this boundary circulation would look like is, well, I've got to think about thumbs and swirls, etc., and it's gonna do this. Right, so there's my there's the circulation, the boundary circulation on the whole surface. Okay, now I want to think about one piece at a time. Let's think about the left side only. Left side only, looking just at this here. Well, again, thumb, swirl, all that business. We're going to have the same boundary circulation, except now we're also going to have that, because that is part of the boundary of S1. Right? And now let's look at the right side. And again, thumb, swirl, etc., etc. That's going to be, well, same kind of a thing, except, now it's also going to have that, because after all, that is part of the boundary of S2. Everybody on board? Everybody with me? And so now, did it work? Is the whole the sum of the parts? Is green plus blue equal to purple? And again, there's a lot of stuff lining up very nicely. This lines up just fine. That does. That, everything lines up just great there. The only discrepancy, the only thing that's not clear if it's lining up, is this right here. And again, same deal as we had before. There's a single curve there that's appearing twice. Circulation, line integral along that curve appears twice, but with opposite orientations. So these two bits of line integral are negatives, so they cancel, and therefore there is no discrepancy. The whole is the sum of the parts. Everybody okay with that? Notice how it's the exact same. I mean, again, the details are different, right? But it's morally equivalent to what we saw with Green's theorem. It's morally equivalent to what we saw with the divergence theorem. It's morally equivalent to what we saw with the two-dimensional divergence theorem. It's really morally equivalent to what we saw with the fundamental theorem of calculus, the fundamental theorem of line integral. It's the same basic idea in all of these cases. And I present these theorems from this point of view so that you can see how it's the same thing over and over again, so that hopefully you'll digest and internalize the idea that, a lot of the same ideas apply, a lot of analogies apply between these theorems. Okay. All right. Right. Erase. There we go. Okay. Right. So, here we go. Boundary circulation. Right? Keyword boundary. Make sure it's, again, this only makes sense if you're talking about boundaries. The whole is the sum of the parts, as we just argued. Multiply and divide by length here. And what do we end up with? We end up with what appears to be a scalar line integral. And then there's this looming question of what is this integrand? Now I'm going to do something a little bit different here. In the notes, I take a digression and talk about what that integrand is and how to think about it, and long and challenging discussion here. Rather than that, what I'm going to do is I'm going to skip these next pages for a minute, and I'm going to come back to that topic after we let's just write down the result to start off. See the resulting theorem, get an example done, get a win on the win column, and then we'll come back and talk about what I just skipped. Okay. So anyway, here we go. This is where we were. Right? We had multiplied and divided by length, thus making this a surface integral. I think I misspoke and said line integral previously. Sorry, it's a surface integral. And the question, again, is what is this? I don't know why it keeps going to the pencil. What is this thing right here? Bunch of details that we'll come back and talk about in a minute, but I claim that what that is this right here. It is curl dot normal vector. As it turns out, curl dot normal vector. Again, much to say about that. That we will come back to. But it's curl dot normal vector, and look where that leaves us. Let's see if I can get the stylus working again. Let's see here. Oh yeah, I'm all charged up again. Okay, let me put this back in here if I can find the... Boom. Okay, all right, we're back in business. Check this out. What's the deal with that normal vector, and doesn't that mess us up? Actually, it doesn't, because... whoops, where is the button? There it is. Normal vector, normal unit vector, that is, times the ds scalar is ds vector. And that's just a flashback to section 15.5. That was our definition of the ds vector. So while it, at a glance, initially looked like it was going to be a scalar surface integral, in fact, it's a vector surface integral. It's a flux, which is pretty weird. So here's the punchline. The theorem I claim should be thought of this way. This is the deep down fundamentally, what does Stokes's curl theorem say? It says that circulation is a flux of circulation density. And I'll come back and talk again next time, but we won't have time today. But I call this specifically oriented circulation density, and that's a whole conversation. So sure, circulation is a vector line integral around the boundary. Yeah. Sure, oriented circulation density is curl. Again, conversation that we're going to have later. So you can think of, in practice, when you write down Stokes's curl theorem, this is what most people write down. Yeah, absolutely. But for comprehension purposes, for intuition purposes, I think this is the best one, best point of view. Okay, now, again, lays out on the diagram exactly as we spec'd. Curl, the operator that we put there, the operator that makes all the good things happen up here, is also exactly the operator that, when you look at a boundary and do a line integral, gives you the resulting flux that gives the same value. Okay. Let's see here. I'll tell you what. Why don't we draw the line right here, rather than me try to squeeze something into 20 seconds, which will never happen. We'll draw the line right there. We'll pick up here on tomorrow, Friday, and see y'all later. Okay, have a good one.